Hi, welcome back to AP Physics C Unit 5. This is our rotational kinematics and rotational dynamics video topic. In this one, we're going to talk about the effect of Newton's laws on rotation. Okay, and you'll see that we have two laws, right? We're going to focus on first and second law. So whenever we have a system exhibiting rotational inertia, or excuse me, rotational equilibrium, that means there's going to be a constant angular velocity. Okay, and it can be without being in translational equilibrium and vice versa. So when we did it way back in Unit 2, we created what are called free body diagrams. Now we may have to create what are called force diagrams, or sometimes I refer to them as rigid body diagrams. Okay, equilibrium doesn't change, right? It's still talking about how the sum of something is going to equal zero. Newton's first law tells us that the sum of the forces is equal to zero. Okay. In this topic, right, Newton's first law of rotation tells us that the sum of the torques equals zero. In fact, these two conditions, right, sum of the torque equals zero, sum of the force equals zero, creates that true static equilibrium. So for an object to be in true static equilibrium, these two conditions have to be met. Okay. If one of those two is not met, then it is not in equilibrium because it is being accelerated in some way. And now what we do, so that is our first law, right? That is Newton's first law of rotation. What about the second law? Well, the second law, when we talked about it in linear, the focus was sum of the forces equals m times that. Well, guess what? There is a rotational equivalent of mass. There's a rotational equivalent of acceleration. So Newton's second law of rotation, or in rotational form, tells us that the sum of the torques equals I times alpha. Okay, so this is Newton's second law of rotation. Okay, and so when you exert a torque on an object, or when you exert a force on an object causing rotation, you exert a torque on it. Okay, if you exert a torque on it, you now are accelerating the object. So when you get these problems, when you get these rotational dynamics problems, you may have to create multiple force diagrams, whatever you want to call them. You will definitely, so they like these with Atwood machines, and you can kind of see this picture here in the bottom right of his diagram. Now what happens with Atwood machines, so if I have an Atwood machine, way back in Unit 2, right, this did not matter. The pulley did not matter. Now here in Unit 5, that pulley will matter, okay? How do you know it'll matter? Is it'll tell you that it has a mass of something and a radius of something, or it'll give you the rotational inertia of it. So if you have a scenario like this, you have three free body diagrams. You have one for the left, you have one for the right, and then you have one for the pulley. Okay, but they all match up. They all have connecting pieces, right? Torque 2, torque 1. Okay, the masses will accelerate linearly, okay, towards the heavy one, and the pulley will accelerate in that same direction rotationally. All right, so let's look at an example problem. So we have a solid disk of unknown mass and known radius r is pulled as a pulley in a lab experiment as shown above, it's actually below. A small block of mass m is attached to a string, the other end of which is attached to a pulley and wrapped around it several times. The block of mass m is released from rest and it takes time t to fall the distance d to the floor. Calculate the linear acceleration a of the following block in terms of the given quantities. So this is a derive an expression question. One thing, typically on the AP test, they will give you this information. So for a disk For some reason in the picture I don't have it, but I for a disk is 1/2 mr squared. Okay, that's going to come into play because when we do our summing of the forces and summing of the torques, we need that. Okay, so let's create our free body diagrams or our force diagrams. So we have, for the hanging block, we have the weight down, we have tension up, and then for the pulley, right, we do have to write its weight component on there, and it has tension, but essentially note that this does not create a torque because it's at the axis of rotation, right? I'm not saying that the sum of the torque is equal to 0. I'm saying that the FG does not create a torque because it is sitting at it's drawn from our axis of rotation, okay? So let's do right? So again, draw, sum, solve, right? Draw a free body diagram, force diagram, sum the forces, solve for what we're looking for, okay? So now let's sum the forces, right? So we know the sum of the forces is M times A, right? And we have two forces. We have Fg minus T equals Ma. And remember, we always put our positive in the direction of the acceleration. So that block's going to go down. The pulley is going to rotate counterclockwise. And so we would just say T equals, so plus minus Mg minus Ma. Okay? But we're looking for A, but we don't have T. That's where our torque side comes into play. So we will say the sum of the torques is I times alpha. So there's really how many potential forces are creating torque? There's two. So we have the torque caused by the tension minus the torque caused by gravity equals I times alpha. But understanding that this creates no torque because it's at the axis of rotation. So we have R times T equals I alpha. Okay, I'm going to substitute in I in for I, or I'm going to substitute in 1/2 mr squared for I. Alpha is given to us in the relationship of A equals R alpha. So alpha would be A over R. So now I just substitute in all of my things. So I have 1/2 mr squared times A over R. And then we can simplify here. One of those R's is going to cancel that R. This R is actually going to cancel the other R. And so I get tension is 1/2 Ma. All right, so now I have T in terms of M and A. Plug that in over here. I get 1/2 Ma equals Mg minus Ma. Add Ma to both sides. So you end up with 3/2 Ma. M's cancel out. So we have G is 3/2 A, but we don't want that. We want A. All right, so A, the acceleration is going to be 2/3 G. Now, does it make sense that it's less than gravity? Yes, because now that mass, the pulley matters, so it's going to be tugging on the object and fall. Okay, so they may ask you, if this is a free response question, they may go further and ask you about, why does this make sense type thing. Okay. All right, so now we're done with Unit 5. We will move on to Unit 6, which is the second half of rotation, which will focus on conservation laws.